Welcome to module 3 of chapter 3 on high frequency behavior of electrical components. Now in this module we will look into the behavior of real mechanical switches, how they produce noise, what are the noise suppression techniques, and about the transformers, real transformers. Here transformers, what is meant by is the instrument transformers, the kind of power supply transformers you can find for converting AC to DC. So, this type of very small transformers. Now, take the case of a mechanical switch. So, normally you have a switching element here. This is the switch element. Then feeding from the source you have some circuit, and that circuit will have some resistance, inductance and capacitance value, and you have some loads that is controlled by the switch that will have some resistance, inductance and capacitance value. So, source side is 2 and load side is written as 1 here. Now, these are resonance circuits. If you look at the possible resonant frequencies, you can find at least 3 frequencies here. One is a resonance in the load side C1 and L1, a resonance frequency of 1 by 2 pi root L1 C1. Another is on the source side 1 over 2 pi root L2 C2, that is F2, and F3, a combination of the load side and a combination of source side and the load side. So, L2 and C1. So, likewise you can find several resonance frequencies, and usually R2, L2 and C2, these are far less than these values, because these are load, more intentional. These are mostly represented by the parasitic elements leading up to the switches. So, I am talking of the switch and the connected circuitry that are required to mount the switch onto a bus bar or some other things. So, since source side values are smaller than load side values, F2 is greater than F1. F1 is the load side resonance frequency. So, that will be smaller than the source side. Now, the switches are in the form of solid metallic contacts. It can be air at atmospheric pressure, there can be pressure switches also. And when the switch is opening, this is the most important thing, there is a variable gap length between the contacts. Switch have certain operation speed controlled by the springs. So, as the time is increasing, this opening of the contact also is changing. So, it is a dynamic gap. So, you have spark gap, parasitic elements and load characteristic. Then this creates an instantaneously varying voltages across the switch contacts V2 and V1. So, depending upon the V2 and V1, you may have arcing, because the switch there is an arc voltage being developed here. If this gap length is above certain value, you can produce an arc. So, that will produce additional noise in the switch. So, let us look at the voltage time relationship for contact breakdown. So, this is a mechanical switch. So, in small air gaps, you have certain voltage applied across this air gap of the switch. The air gap length is varying, or you can express in terms of length. Say for example, this is 1 micrometer, this is 10 micrometer, this is 1 millimeter distance of gap. Or it can be, if you have certain speed for opening of the switch, it can be in terms of time also, this axis. So what is expressed here is a voltage time relationship, a composite breakdown characteristic that is being expressed here. So it is a voltage time relationship for contact breakdown. So we are not going into the theory of contact high voltage physics or anything like that, but there are phenomena like glow discharge breakdown and arc discharge breakdown. So it is enough to say that glow discharge breakdown happens at much higher voltage, around 300 volts or so, and above that you have a glow discharge happening. And if you can have an arc discharge breakdown if the voltage is going much higher, then after the arc discharge breakdown, suddenly you establish a current across the switch contact, and then to maintain that current you don't require as much voltage. So that voltage, it is depending upon the arc resistance, that is the arc discharge sustaining voltage VA, and that is shown here. So it is around a little more than 10 volt for most materials. So above this value you have a sustained glow discharge, and above this value you have, and once arc is formed, you have a sustained arc discharge voltage. So ideally you want to operate the switch below this curve. This is a composite breakdown curve. If you are below this curve, if you are suppose you have a voltage versus time, instead of meters we write time here, because if it is at constant velocity, if it is traveling, you can translate into time. So if you have a curve like this, say like that, it will never go into breakdown. So you only have this normal oscillation associated with resonance circuits and all. But if you go above this, then you will have a breakdown, either glow discharge or arc discharge. So then you will have noises associated with switches. So the contact breakdown and arcing, if the voltage across the contact Vc equal to V2 minus V1 is greater than the breakdown characteristic, this heavy line. Below that you do not have that breakdown. Now contact arcing voltage and current values for common materials are shown. To extinguish the arc, the voltage or current has to be brought below the arcing value. This is easier in AC operation because of the natural zero crossing. So for silver it is around 12, and the minimum arcing current IA is around 400 milliamps. So for other materials it is slightly higher. So you have to make sure, to extinguish the switch, you have to make sure that the arcing voltage is below this value, 12 volt, and arcing current is below this value, 400 milliampere. Then you can extinguish the arc. So this shows we have seen this curve before. This is without breakdown at the contacts, just oscillation due to this resonance circuit, damped oscillation, but this is with restrikes at the switch contacts, because periodically there will be arcing, extinguishing, then arcing, extinguishing, etc. will be happening as V2 minus V1 is changing. Now, avoiding contact breakdown, keeping the contact voltage below the composite breakdown characteristic, below around 300 volt to prevent the glow discharge. If the breakdown happens, force the current available always below that for sustaining the breakdown, that is keeping the initial rate of rise of voltage below the value necessary to produce an arc voltage. So, the rate of rise of voltage is very important in forcing the current available below that value. Say a value of 1 volts per microsecond is usually sufficient for most contact. So, you keep it below that value, then you can prevent arcing. Now, noise suppressions and contact protection. Switching produces arcing, and this arcing can create high frequency radio noise. Say from in old fashioned tube lights, the starters and the chokes will produce high frequency noise, and the noise can be suppressed by having a shunt capacitance. Yeah, but then once the shunt is short circuited, then it is a 0 value. It kind of bypasses completely the switch. This is a modified form of the circuit with a resistance R also, and this is with a diode connected across the resistor for better performance. So, several variants depending upon the cost, you can find several variants of the circuits in arc suppression for the contacts. Now, transformers. Transformers have a iron core, and you can have a primary winding and a secondary winding, and normally they are 4 terminal devices, but for the purpose of noise transfer you can consider is a 6 terminal device, because you have a reference or a ground. So, transformers are 6 terminal device, and depending upon you have several parasitic elements between primary and secondary, across the primary, across the secondary, primary to the core, secondary to the core, core to reference, primary to reference, secondary to reference, etc. You can have common mode to common mode transfer. You have seen in the first class what is meant by common mode. There the currents will be in the same direction, and differential mode to differential mode transfer. Differential mode is when currents are in the opposite direction. So, this now suppose the core is not connected to the reference. So, this will be the capacitive network. Now, this is the model, and you can simplify the model if the core is connected to the ground or not connected, or primary is only connected to the ground, or the secondary part is only connected to the ground. You can get different circuits. So, let us do some analysis of the circuits. So, our purpose is to avoid surge transfer across windings. So, there are two ways. One is connect the core to the ground and use the conducting foil. So, we take common mode to common mode transfer. So, what happens is that if the core is not connected to the ground, this is the capacitance across the windings, primary to the core PC, secondary to the core SC, and core to the ground. So, this will be the kind of a network for capacitances for common mode to common mode transfer. So, 1 and 2 are the same terminal here. Then if the core is connected to the ground, it shorts out this capacitance and it shorts out this capacitance also. So, you have kind of these two capacitance are in parallel now, CPC. So, you just add up those capacitance, CPC plus CPR. These two capacitance are in parallel. So, you add up those capacitance. So, you get a network like this. And now you can analyze how much transfer of noise will happen from primary to secondary or secondary to primary in the case of common mode. So, this will be the circuit to be used. Now, use of metallic screen between primary and secondary, reduction of common mode to common mode transfer. Now, if a foil is used between the primary and secondary, then you can, if you take this capacitance now between primary and secondary, this capacitance you can break into two halves if you use a foil. So, one part is primary to foil and the other part is secondary to foil. So, these are connected together. So, you can see that there is no direct transfer between primary to secondary, the transfer is to the ground, and these two becomes parallel. So, it is just added to this. So, screen connected to ground ideally eliminate the coupling capacitance CPS. So, if you have a carefully installed screen, it can reduce coupling capacitance to as low as 1 picofarad. Without this screen, CPS is usually many tens of picofarads. So, screens can be quite effective in eliminating common mode to common mode transfer. Now, differential mode to differential mode transfer. So, there you have to consider this winding also, CPS, primary to secondary capacitance. Now, core is directly connected to the reference. So, if you take this one, then core is connected to the reference, this two becomes parallel, this two becomes parallel. So, you just add it up. And those two are connected in series, it comes like that. So, this will be the circuit. So, how do you reduce DM to DM transfer? So, CPF and CSF in the previous CPS is the one. So, if you can split it into two parts, say if you have a screen connecting the primary to the ground, then you split this capacitance into two parts, and one part is connected directly to the ground and this also is connected to the ground. So, you are eliminating the transfer from the source side. Still from the secondary side there can be some transfer. Screening can also reduce high frequency DM-DM transfer. In this case, the foil surrounding the winding is connected to either the primary side or the secondary side, and not to the reference, depending on from where the noise is originating. The transformers are commercially available with 3 screens, usually one to control CM-CM transfer and one on each side to control DM-DM transfer at high frequency. So, one to primary and one to secondary, and one for core mode transfer between primary and secondary. So, there can be up to 3 screens in a transformer. The DM screen increases the capacitance between terminal 1 and 2. Usually that is not any big problem. The absence of DM screen, external shunt capacitance can also be used to reduce DM transfer. That is just by shunting the noise like a noise filter. So, that will be more cheaper solution than providing screens.